Welcome back. So we continue the discussion of this I oscillation and eigenmode, where initially we looked at the spring mass damper system, and then we are talking about this 2 degrees of freedom or more than 1 degrees of freedom system, where your displacement could be a vector, and you essentially deal with this kind of metric system, and the solution vector could be found using Rayleigh method. So now we have already looked at, based on the guess values, this Rayleigh method can be quite accurate for estimation of this frequency of oscillation. Okay. Now, what we would like to look at is the error of Raleigh's method. So we can estimate the error of Raleigh's method. Okay. So what we can say that assume, let's say omega naught, which belongs to a real number, and omega naught belongs to Rn, are the true eigenpair. So that means what that is, they satisfy. Once we assume that this omega naught and omega naught are the true eigenpair, then they satisfy this equation k w naught omega naught square m w naught. Okay. Now, what, let's say w, the actual eigen vector, is w naught plus delta w, and where delta w is the error in our guess. Okay. So what we get then, essentially, what we get, omega square, which is half of w bar transport k w bar, half of w bar transpose m w bar. So this is f of w bar. Then what we can have, half of w naught transpose k w naught m w naught. So this is f of w naught square plus this is w naught transpose into del w square. So what we have here del f of w naught is half of W naught transpose Km W naught K W naught, half of W naught transpose K W naught M W naught, half of square, which is K W naught minus omega naught square Km W naught, half of W naught transpose 0. Okay. So what we so the error that you have, that is omega square omega square omega naught square plus W square, which is essentially order of I mean is essentially second order uh, error. Okay, so we now we can see for now different example. We can see, let's say we have x1, this is m2, x2, this is k2, this is k1. So this is m2 x2 double dot k2 x2 minus x1 0, m1 x1 double dot k1 x1 minus k2 x2 minus x1 0. So my either the vector W vector is x1, and so this belongs to R2. Then if we write down the matrix equation, this would be m1 0 0 m2 W dot k1 plus k2 k2 minus k2 W equals to 0. So this is nothing but m, which is belongs to 2 by 2. This is belongs to K matrix, also 2 by 2. So here two different system. What you can see is that, so similarly we can look at another example where let's say m1 x1, which is k1 m2 x2, which is 2 millimeter, let's say 1 millimeter, this is k2. Okay, this is another system. Okay, so what you can see is WT is W bar e to the power j omega t. You can assume M2 greater than M1, K1 is K2. So this is 1, 2, which are the eigenvector or eigenvector. Then we have Wt j omega t 2 into j omega t. So what we can have, kinetic energy would be half W bar transpose mw bar m1 plus 4 m2 omega square a naught square. So now this is the kinetic energy expression that you get. Then what you have is like potential. Similarly, we can find out the potential energy. Uh, that would be half of W bar transpose kW bar. Okay. So here, what we can do now, we can find out the potential is kW bar. So this one can write half of A naught square 1 to transpose K1 plus K2 minus K2 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 1 2 half of A naught 1 to transpose K1 plus K2 minus 2K2 2K2 half of A naught K1 minus K2 plus 2K2. So which is half of A naught K1 plus K2. So omega square is K1 plus K2 M1 plus 4 M2 K2 by 4 K1 by 2 by M2. So this is the estimation for the kinetic energy. So that's how you get. So we have looked at two different examples of multiple degrees of freedom and finding the eigenvectors and estimating the kinetic energy and potential energy, things like that. So these are all what we are looking at. It is that first, I mean the basic structural analysis in terms of static beam equation. Then we see that how that gets applied to the rotor blade. And then we look at the basic vibration analysis for a single spring mass damper system, and then 2 degrees of freedom spring mass damper system. Uh, from there, we would extend this analysis to other we call the other rotor blade thing. And now what we would look at it the dynamic beam equation. Okay. So now we'll look at the dynamic beam equation. Okay. So we start with dynamic beam equation. Okay. So we have earlier seen the Euler-Bernoulli equation. Now this is a combination of Euler-Bernoulli and Lagrange kind of produce the dynamic beam equation. So obviously, since it's a dynamic beam equation, this depends on time, and hence the equation can be written as del 2 by del x2 e of x I of x q of xt minus mu of x del 2. So that is what is kind of represented as dynamic beam equation. So here what you have mu of x, which is mass density per length q of xt, which is distributed load, omega of xt, which is time varying solution, no damping. Okay. So what we have essentially, if we look at it, this goes like that: x equal to L, and this is W of xt. This is x equals to 0. Okay. So this particular dynamic beam equation that we have, this is a linear partial differential equation. So after special discretization, we can have k of w m of w dot. So essentially, where E of kinetic energy 0 to L m of x del by del t square into dx, and elastic energy half of 0 to L Ex del 2w by del x2 square dx. Okay. So that means from the dynamic being equation, one can estimate the kinetic and elastic energy as well. Uh, Now we can find out tower eigenmode because both tower and nacelles have mass. Okay, so obviously one can look at like this, where so this is kind of a lowest eigenmode, and one can see is the second lowest eigenmode. So so here, since both tower and nacelles have mass, so one has to compute so the eigenmode. So one needs to compute eigenmodes for a very unequal mass distribution. So this is how the two lowest eigenmodes may look like. Okay. So now what essentially we're trying to say here is that now again now we are extending our fundamental analysis of vibration to our rotor blade. But along with that, there is a structural constraint here because the tower and the nacelle, they are also having some mass. So which is kind of represented here, which is just like an hammer with a rod and with a hammer, but they are having some kind of an oscillation. So their eigenmode needs to be also considered. So I mean, later on when we'll talk about the linearized model and all this analysis for that, so the idea what we are talking here is that initially look at this basic example of calculations of this frequency and all these things, but later on then considering the aerodynamic forces, we look at the simplified model to analyze all these things. So this is for the tower eigenmode that we have talked about. Now we can estimate this the kinetic energy and potential elastic energy using this dynamic beam equation. So here the issue is that the whole structure along with the root is exposed to dynamic loading. So that is why they need to be taken into consideration. So now the kinetic energy is half of mu x uh, xt by del x2, del t square dx, and elastic potential energy E pot or E elas half of 0 to L E of x I of x uh, xt by del x2 square dx. Okay. So for this, let's say assume omega xt is omega bar x into e to the power j omega t, with omega bar x is e naught x square by L square. So this is for a rough approximation of the lowest eigenmode and assuming constant mass mu x, ex, and ix throughout the tower. So what we'll get now, we can using Rayleigh's method uh, Rayleigh's method uh, we can get E kinetic energy is omega square half of 0 to L m tower A naught by L square dx m nacelle A naught square. So what we have kind of done here, if you see, so one component this coming from tower, and this is the component coming from nacelle. So both the component of this the whole unit, they are now considered, and since they are exposed to this dynamic condition, so we try to estimate using this dynamic equation and estimate the kinetic energies and elastic potential energy. So important point here to note is that not only the rotor blades and all these things, because of the wind, also your these things get exposed, the structure and the other thing. So we'll finish this discussion or continue this discussion in the next session. Thank you.